Welcome back to BCIS 1305. This is Dr. Schuessler again, and today we're covering the last chapter in our text, Chapter 12, Information Systems and Program Development. So the stuff we're going to be talking about in this chapter is we're going to talk about the system development life cycle, the processes that are involved with that. We'll talk about guidelines for systems development. There are some general guidelines that we really need to take into consideration. We'll talk about some of those. We'll talk about the importance of project management and feasibility assessment. Project management is a particularly important area of emphasis because we tend to run over budget, and we tend to take longer, and the projects tend to not do what they're supposed to do. So we really need to do a better job of that. And we start out by talking about it and become educated about it. We'll talk about feasibility assessment. Feasibility is something that most people are pretty aware of, but we really kind of break it down to look at very specifics in terms of feasibility, economic feasibility, technical feasibility, for example. We'll talk about the purpose of and tasks conducted in each systems development phase. We're going to differentiate between low-level languages and procedural and object-oriented languages. We'll talk about some of the other programming languages and application development tools that are out there. And then the chapter finishes up talking about different ways to develop web pages, specifically focusing on things like scripting languages and stuff like that. So let's go ahead and dive on into the chapter. So systems development is a set of activities used to build an information system. Now remember, an information system is a combination of hardware, software, data, people, and procedures. So it's not just the computer. It's a combination of the computer and the people and procedures that interact with the computer and that technology. Systems development activities are grouped into phases, and this is called the systems development life cycle. Depending on the text that you're reading, there'll be different phases, different number of phases, and different names for those phases. But in general, there's a lot of similarities from one text to the other. And we'll go through that when we get to it in the next few slides. So this is kind of a graphical representation of what the systems development life cycle might look like. Here they show 5 stages. Like I said, in general, you're going to have anywhere from 4 to 7, depending on the text. Planning, analysis, design, implementation are all pretty commonly seen, regardless of the text. In some cases, that last one will be referred to as implementation, but in this text it refers to it as support and security. Couple things I want you to note. I want you to note that the arrow between step 5 or phase 5 going back to 1. And this signifies the fact that you're never really done with the systems development process. In other words, once you've completed a particular, the development of a particular solution, it needs to be updated. It needs to be changed. Eventually it will outgrow its usefulness and you'll have to develop a new system. So this is a never-ending process. So if you have that tendency to want to be done, you realize this is not the kind of thing that you're ever really done with. There's also these grouping activities that you see here in the middle, and these include things like project management, feasibility assessment, documentation, and data and information gathering. And these are things that are done throughout the process. Project management keeps each one of these phases going and keeps you moving from one phase to the next phase. Feasibility assessment says, okay, do we need to spend more time going back to analysis and design because maybe something is not feasible and we need to figure out a different solution. We're constantly documenting what's going on. As changes end up being made, we offer support, and users suggest that we need to make certain changes. We need to be sure to document those changes. And then lastly, data and information gathering. We're constantly gathering information from users about what their needs are, what their data needs are, their performance needs, etc., so that we can make enhancements and improvements to the system. So there's lots of different guidelines that we need to follow, but we can generally talk about these 3 as being extremely important, or being the most important perhaps. In general, we're going to break up and group activities to group similar activities together. In other words, we're going to take kind of a top-down approach. We're going to take a big problem, we're going to break it up into chunks, into phases, to be able to tackle those individual chunks and be able to accomplish something. If we look at the system as being this huge, monstrous problem, we'll never be able to get it completed. But by breaking it up into smaller pieces that are more manageable, we can start to make progress and get through the process and actually get it developed. We need to be sure to involve users. A lot of projects fail because we have a tendency, coders have a tendency, I should say, to hear about a problem and then want to go code. And the reality is we need to stop and talk to users first. We need to find out exactly what it is that they need. What is the solution that they need? What are they trying to do? And by involving users throughout the development process, we're much more likely to get user buy-in. We're much more likely to understand what their requirements are. We're much more likely to develop a solution that's actually going to address their needs. And they're much more likely to use the product because they were involved in its development. And lastly, we need to define standards, especially if we're in a very large organization. We have different departments that are developing different solutions to problems that they face uniquely within a department. If we don't have standards, if we're not following those standards, we may be developing solutions that are incompatible with each other. And if at some point in the future we want those two different programs to be able to talk to each other, if we've defined standards, that's going to be a much easier process than if we weren't following any sort of standard. So as we were talking about earlier, we want to involve users. It really doesn't matter where they are in the organization. If they're involved in a particular system, if they're going to use it and be exposed to it, we really need to talk to them. So whether it's steering committee members, corporate level executives, users, vendors, all of these people have a vested interest in the system. And so we need to talk to them and see what data do they need, what are the types of reports that they need, what is it that they need to track, what are their performance needs, etc. As far as project management is the process of planning, scheduling, and then controlling the activities during systems development. To plan and schedule a project efficiently, the project leader identifies the following elements: the project scope. In other words, how big or small of a project is the project. This is important because when users start to ask for the project to do something else, something that falls outside of the project scope, we have to recognize this and say, no, that was not our mission for this particular project. My personal approach to this would be, you don't necessarily just say no, you should treat it as a negotiation and make them recognize that if they want to modify the scope of the project, that it's going to require X amount of dollars more to be able to implement this new feature. It's going to take X amount of time to be able to implement this new feature. So you need to communicate the effects that it's going to have on the scope and allow them to make the decision, or allow the appropriate person, the appropriate decision maker, the opportunity to say yay or nay on that particular modification to the scope. You need to be able to identify the required activities. So what are the various tasks that need to be completed to be able to complete a project? Once you've done that, now you can start to make estimates regarding the time and the cost for those activities, as well as start to order those activities. Which ones have to be done first? The example I used in class was, if you're building a building, you're building a house, you can't really hang a sheetrock, for example, at the same time that or before you've put up the studs to the house. There's nothing to hang them on, so you have to have the studs in place before you can hang the sheetrock. In some cases, activities can take place at the same time, though. You may be able to put up bricks, to brick the outside of the house while you're hanging sheetrock. The studs are already up. You certainly should be able to do that. So these are some of the things that you do with respect to project management to be able to keep it on time, on budget, all those types of things. So these are some of the tools that you might see when you use project management software: Gantt charts, PERT charts, etc. There's Microsoft Project is probably the standard when it comes to this, but there's other solutions out there. For example, Gantter is a cloud-based solution that's freely available. It's not as full-featured as Microsoft Project, but it's very nice. You've also got a number of templates that are out there for Excel and things like that. One of the things that I think intimidates students is they look at a lot of the reports that you can get out of Microsoft Project, and they think that this requires an awful lot of work. But you can really boil it down to some very basic information. If you look at this right here, this is really a work breakdown structure. So you list the different steps that you've got. You've got subtasks. You've assigned durations to them. You've identified predecessors where this task must be completed, task 2, step 2, must be completed before you can do the next step. So this is the important information. You put all this information in. This is automatically generated based on this information. This is automatically generated based on this information. So a lot of it is the exact same information, it's just presented in different ways. So it can be very powerful. You can get a lot of information without necessarily quite as much work as what a lot of students tend to think of. We talked about feasibility earlier being more complex than just the term feasibility. We may need to consider operational feasibility, or schedule feasibility, technical and economic feasibility. These are all different ways that a project may or may not be feasible. Operationally, it may not fit within our organization, a particular solution. We may not have the time to implement a solution. We may not have the technical know-how. We may not have the money. So there's lots of different kinds of feasibility that we need to be aware of. We also need to document the process. Every time we make a change to the system, every time we're moving the project forward, we need to document that and collect all that information and keep it in some sort of organized, centralized repository. It can be tedious. A lot of people do not enjoy this process, but it's really important to make sure that we maintain up-to-date documentation. When a user comes to us in the maintenance phase and suggests a change, we need to be able to go back to that documentation and update it so that that documentation reflects those changes. During the systems development process, members of the project team gather together to gather data and information using several different techniques. This is where you're going to go out and you're going to talk to users. You're going to look at a lot of different documentation. So, for example, you may pull up invoices that the organization has. You pull up vendor information. You pull up receipts. You pull out marketing information. You pull out all kinds of documentation and look at it to see what kind of information is being used. You observe processes that are going on. How are orders taken? How is payroll distributed? Things like that. You may do surveys. You survey vendors, survey employees, survey customers. Again, you can glean a lot of information from what they feel like is working and what perhaps is not working so well. You can interview them. You get a lot of very rich information by doing that. Join application development sessions. You can do research. You can look at competitors. So there's a lot of different ways to gather information, but this is a very important phase because if you miss something here, your design is going to be flawed. So this is very important, very tedious, but it's a very important phase of the systems development process. Then you can move on to the planning phase. Once you've done that, you can actually start the planning phase, which begins when the steering committee receives a project request. You get 4 major activities that are going to be performed. You're going to review and approve the project requests. Not all projects are going to be approved. You're not going to move forward from there in some cases. You're going to prioritize the project request. Not all projects are created equally. An organization may have lots of different projects that they need to work on, but some are going to be more important to the organization than others. Some, for example, may be mandated due to regulatory requirements. Others may be really important from a competitive perspective. Yet other projects may simply be more for convenience. This is something we'd like to be able to do. So you need to be able to prioritize so that you can tell which ones you need to work on first. Then you're going to allocate resources. You've got to devote money. It's not enough just to say, okay, we're going to do this project. You've actually got to pay for, provide those resources for that project to be able to be done. And then you need to form a project development team to actually do the work. Then you can move on to the analysis phase. In general, you're going to have 2 major activities here. You're going to conduct a preliminary investigation to determine exactly what the nature of the problem is. What is it that needs to be fixed? What needs to be improved? A great place to start here is talking to the person that submitted the request. What is it that they observed that's not working the way they feel like it should work? Then you can dive more into more of a detailed analysis. Start looking at the current system. Is there a disconnect? Perhaps that user that submitted the request doesn't know how to use the existing system. You need to look at that. Maybe maybe it's an issue of training rather than needing to develop a new system. But under the assumption that the new system does need to be developed, look at the current system. How is it working? What is it that's not working correctly? Determine the user's wants, needs, and requirements, and then recommend some sort of a solution. The text goes through an example and gives you an idea of what the request might look like, or what the document might look like. Not something overly big or complex. Again, this is really a pretty preliminary document at this point. The system proposal is going to assess the feasibility of each alternative solution. In other words, each solution is not necessarily going to have the same feasibility, the same economic feasibility, the same time feasibility, etc. So some of the different choices that we've got: we can potentially modify the existing system, we can buy retail software, we can use web apps, we can build custom software, or maybe we outsource. Each one of these has a different feasibility to it. For example, outsourcing may be much more feasible in terms of time, in terms of technical feasibility, because we're paying somebody else for their technical expertise. But economically, it may not be feasible. It may cost too much. Building custom software may be economically feasible. We have the employees that build software. They may be able to do it, but they may not have the time, so the time feasibility may not be there. So we need to be able to evaluate these different alternatives. The design phase consists of two major activities: acquiring the hardware and software, and developing all the details of the new or modified information system. So the purchasing side is acquiring all that hardware and all that kind of stuff. We need to identify the technical specifications. How many servers do we need? What are the performance characteristics? How much RAM do they need? How much hard drive space do they need, etc. We can solicit vendor proposals, identify several vendors, have them bid on our particular solution. We may not simply be focused on price. We may be focused on support as well, so we need to keep that in mind as well. We need to be able to test and evaluate the different vendor proposals, and then ultimately we need to be able to make a decision on one specific proposal. On the software side of things, we need to develop detailed design specifications. We need to look at the database that we talked about last week. What tables do we need? What attributes do those tables need to have? What kind of data validation do we need to do? We need to look at input and output design. What are the forms and reports that are going to be needed? How do they need to look? How do they need to flow? Things like that. So talking to users a lot is really important in that area. And then lastly, program design. How are we going to make the processes work to be able to input and output data for our database? System analyst is typically going to develop two types of designs for each input and output. They're going to have a mock-up and a layout chart. The layout chart is going to allow them to manipulate where the fields go. It's going to give them information about the names of the fields, things like that. Whereas the mock-up is going to give some example information for users to be able to look at and kind of visualize how the form is going to look. From that, we can develop a prototype, which is really a proof of concept. It's kind of a working model of the proposed system. Now, a model is a scaled down version of what it is you're actually looking at, so it's not necessarily going to be completely working. So that's one of the problems with a prototype. It may prototypes have inadequate or missing documentation. It's not designed to be a completely functioning system. It's designed to give users an opportunity to contribute and suggest changes and suggest modifications to the way the prototype looks, so that the ultimate system does exactly what they want. Unfortunately, one of the problems with a prototype is that a lot of times users see the form or the report as the final product, the completed system, and that's not necessarily the case. In fact, most of the work actually goes into the coding behind the form, behind the report, and so they need to realize that just because they're seeing a lot of forms, they're seeing a lot of reports, doesn't necessarily mean that the project is close to completion. Computer-aided software engineering tools, case tools, are also used in a lot of cases to help development activities occur. These help to really kind of streamline the process and make it much easier for developers to develop solutions for a system. The implementation phase is where we're actually going to go through the process of implementing a system. So if we've done due diligence, if we've done everything that we need to up to this point, this step should really go pretty smoothly. The reality is we need to spend the time on the previous steps because they're very important. They really allow us to define things properly. And if we've done so, this, like I said, the remaining steps should be much smoother. If we're spending a lot of time on implementation, chances are pretty good that we didn't do a very good job earlier on in the systems development process. So in the implementation phase, we need to develop the programs and the applications. We need to install and test the new systems. We need to train users, and then we need to convert to the new system. As far as some of the tests that need to be performed, we need to perform unit tests, system tests, integration tests, and acceptance tests. Unit tests are going to test individual parts to our system that we've created. A systems test is going to test the system that we created in its entirety, just that system itself. The integration test is going to test our system that we just developed with other systems that it needs to interact with. And then perhaps the most important test is the acceptance test. Does the system do what the users wanted it to do? Does it solve the problem that they actually wanted it to do? And if we can get them to sign off on that and accept what we've produced, we've met one of our goals anyway. Training involves showing users exactly how they're going to use the new hardware and software in the new system. We've got several different ways of training. These are some of the common ones: one-on-one, classroom, web-based. Web-based is great in terms of efficiency. We can reach a lot of users. We can give them a lot of very rich feedback using web-based training. It's not necessarily the most effective, though. Classroom style tends to be very effective, but it costs more than web-based training. We're not able to reach as many users as quickly and efficiently with the classroom style instruction. One-on-one sessions tend to be very effective, but they also are very expensive relative to the other two approaches. It takes us a lot more time to train the same number of users when we're doing it on a one-on-one basis as opposed to classroom or web-based. Once we've done all that, we need to actually go through the process of conversion, and we've got several different ways of converting from the old system to the new system. We can do a direct conversion, which we shut down the old system and fire up the new system, and that's great as long as it's a low-risk system that we're replacing. If it's high risk, this can be very risky. If the new system doesn't work and the old system's out of there, we've got a problem. We can do a parallel conversion in which we run two systems at the same time, and this is great if the system is extremely important, if we can't afford to be down. This is a good approach, but it also tends to be very pricey because we're having to enter all that information into the system twice, once in the old system and once in the new system. We can have a phased conversion, or we can have a pilot conversion. A phased conversion may be where we pick certain areas of the organization to start to implement the new system, and we phase it through the organization. We can also do a pilot conversion where we only do parts of the program. So there's different approaches that we can take to developing or to shift converting over to a new system. The last step in the systems development process is support and security, and this is where we're going to provide ongoing assistance for an information system and its users after the system is implemented. So this is where we're going to perform maintenance activities. If we need to compress things, for example, if we need to delete old records for performance reasons, things like that. We're going to monitor the system performance so that we know when the system starts to slow down and requires more attention. We're going to address security issues in this stage. So this is an important stage, and again, this is not the end. We're not done at this point. We're constantly monitoring it, and once that performance starts to go down, once the performance maintenance activities start to go up, maybe we need to start thinking about planning the next iteration in this process. So the system that we end up developing is going to be done in some sort of a programming language, and the programming language is a set of words, abbreviations, symbols, etc. that a software developer uses to communicate instructions to the computer or mobile device. In general, we can break programming languages up into a couple of different categories, either a low-level language or a high-level language, and there's a spectrum in between there. Very low-level language is machine language. It's binary. It's ones and zeros. This is first-generation programming language, and this is what the computer understands, binary language. As you can tell, not particularly user-friendly. The next step up is the assembler language, and this is an example of a second-generation language. A little bit more intuitive when you look at the instructions there on the left, but still not very user-friendly. We need some way to convert that to binary so that the computer can actually understand that, and that's where the idea of a compiler comes into play. I'll talk about that a little bit more here in just a second. A third-generation language is a object-oriented language or procedural language. A procedural language is a language in which a programmer writes instructions to tell a computer what to accomplish and how to do it. C, for example, is a programming language like that. And when you look at the code here, you can tell this is much more user-friendly. You can probably not understand the C programming language and still kind of have an idea of what is going on here. For example, up here at the top, we've got comments that have been included to help the programmer communicate what the next line of code is supposed to do. So here we're doing a calculation where we've got RT underscore HRS times pay underscore rate equals RT underscore pay. So it's calculating, in this case, our regular pay. We can do overtime pay, we can do gross pay. So we've got all this information in, and even though you don't necessarily understand the language per se, you can generally get a pretty good idea of what is going on by reading that language because it's a higher level language. Now we've got, as I mentioned earlier, we've got to be able to convert these higher level languages to the language that the computer understands. What was that language? It was binary. Typically, we're going to compile that program using a compiler to translate it into that binary code before executing it. This tends to be a more efficient approach. It allows a program to be understood on a particular system, on a particular platform, but it also cuts down on the portability of that program. In other words, it's compiled to run on a PC, or it's compiled to run on Linux, or I should say compiled to run on Windows, or compiled to run on Linux, or compiled to run on Apple, for example. So it tends to be more efficient on that platform, but it won't run on other platforms. If we want it to run on another platform, we've got to write different code. An interpreter, however, is a little bit different. An interpreter actually takes that code and converts it on the fly as it's being executed. This gives us the advantage of having more portable software. We write the code one time and it can run on different platforms, and that's great. The downside is because it's being interpreted as it's executed, it doesn't tend to perform quite as well, so that it's slower execution time. So graphically, this is what they're trying to represent with that process. An object-oriented programming language is also a third-generation language. It allows programmers the ability to reuse and modify existing objects. Lots of different advantages to object-oriented programming. Objects can be reused, programmers create applications faster, and most object-oriented application development tools are integrated development environments as well. So very graphically oriented, helps to speed up how fast you can create solutions, things like that. So very much more efficient approach to programming. Java is an example of an object-oriented programming language. It was developed by Sun Microsystems. Uses a just-in-time compiler to be able to convert the machine-independent code into machine-dependent code. C++ is another example of an object-oriented programming language. It's an extension of C, and it simply contains additional features for being able to work with objects. Visual Studio is Microsoft's suite of object-oriented applications development tools. And it's an integrated development environment that allows you to develop all kinds of applications in a graphical environment. So here's an example of a Visual Basic Desktop application. I know it's kind of hard to see. I'll zoom in here a little bit. This is the development environment right here, and so you can see that you're dealing with a very graphical type environment here. Over here, if you can tell, you've got different types of things that you can put in this graphical environment. You've got buttons, you've got text box, you've got labels, drop-down boxes, radio boxes, all kinds of things that you can put in. Does that mean you don't need to be able to code? Well, no, not necessarily. You still got code involved, but a lot of the development can be done in a very graphical way. It helps to still be able to code, or still at least be able to understand code, because in a lot of instances you're going to need to be able to make modifications, especially if you're doing anything out of the ordinary. You're going to need to be able to make modifications to that source code rather than just working in that graphical environment. A fourth generation language is a non-procedural language that enables users and programmers to access data in a database. We talked about this last week when we were talking about databases. SQL is a great example of this. Very simple and easy to understand terms and terminology. When you see it, you generally have a really good idea of what's going on. It's easier to understand than even a third generation language. Is it quite English, like speaking English? No, it's not. But it is a very, very easy to understand, easy to follow type of programming language. Going to the other end of the spectrum, we've kind of moved forward into very modern, different types of programming languages. Going back and looking at some of the classic programming languages, there's lots and lots and lots of different programming languages. Some of those included things like COBOL, and Lisp, and Pascal, Fortran, Ada. Lots of different types of programming languages, and they were designed for different things. For example, Pascal was designed to teach procedural programming languages to college students. COBOL is a programming language designed for businesses to help them generate reports and things like that. So there's lots of different programming languages out there. Once you've learned one, you can usually pick up another one fairly easily. The biggest breaks are really more in the area of structured programming versus object-oriented programming. It can be difficult sometimes for somebody that has a good background in structured programming to pick up some of the nuances of object-oriented programming, and vice versa. In some cases, rather than actually generating all the code for an application, we can use an application generator, which is going to take the specifications that we put into the system and create the code for us. A lot of databases, for example, allow you to do this. So you specify your tables, you specify your forms and reports and all that kind of stuff, and it will generate the code for you. And that will allow you to take that program and then go and install it on other systems that may not have the database on that particular program. So it'll create the back-end database for you on that computer. It'll create all the code up front for you for the front end, and allows you to do that automatically based on those specifications. Related to that is the idea of a macro. It's a series of statements that instructs an application on how to complete a task. You can usually record it, create a macro in a couple of different ways. You can record the macro row with a macro recorder, or you can write the macro in the application itself. And here they give you an example in Microsoft Excel of what a macro is, what it can do, and some of the code that's behind the macro. Now, HTML is not really a programming language per se, but what it is a set of instructions that tells a browser how to display content in a text file. So an HTML file, in its truest sense, is nothing more than text information. That's all it is. It's not until you start to include images and scripts and stuff like that that it becomes more complex. But in its truest form, HTML is just a text file. And you can use a program like Notepad or WordPad to be able to create HTML documents. What makes an HTML file more powerful is the use of tags, and those different tags are what tells the browser how to display the contents of that text file. So to bold certain pieces of text, to change the color of the text, to all those different types of things, to underline things, etc. So that's where HTML comes into play in tags. XML is related to HTML in that it's a markup language. But whereas HTML focuses on both the content and the format of data in that page, XML focuses on what that data actually is. You can think of it kind of as a flat database. It's essentially a flat file, and allows you to store information in that flat file and operate in a lot of ways like a database. As far as some of the development languages and tools for websites, here's some examples: JavaScript, Perl, PHP. There's also ASP. You've got other things like Flash or Silverlight from Microsoft. And these allow software developers to write scripts and write applets and servlets, ActiveX controls, etc., to create more interactivity with a web page so that you can have a dialogue, have some interaction with users. And then lastly, the text talks about Ruby on Rails, providing technologies for developing object-oriented database-driven websites. So in this chapter, we talked about the systems development phases and 5 different phases and how it's really kind of an iterative process. We talked about some of the guidelines for developing systems. In other words, you need to do some basic things. You need to involve users, for example. It's really an important concept behind developing systems. We talked about some of the activities that occurred during systems development. We talked about various programming languages and programming development tools. And we talked about web development tools and some of the different scripting languages and all that kind of stuff. So that is that chapter in a nutshell. It's a pretty decent chapter. Covers a lot of content. There really is a lot of content. You can spend a whole semester talking about systems development. In fact, we've got classes just on systems development. So it can be a very in-depth topic. So like I said, there's a lot of stuff in this chapter. If you do have any questions, send me an email. Follow me on Twitter or some of my other social media sites. And that's all I've got for you today. So take care.